Okay. So when you hear the word probability, what do you think about? What is that? What comes to mind? I probably will go to the store.
The chances of it happening?
I've got a chance. So it could happen, or maybe it won't happen. So if someone says probably, that maybe it'll happen, maybe it won't. It's not a certain. It's not like I am going to the store. You want to go with me? No, it's probably. So there's a chance of something happening. There's also a chance of something not happening. So there's two ways that we're going to look at probability. The first one is theoretical, is the theory behind it, is kind of sort of an analysis, very mathematical, scientific type look at things. The other kind would be empirical probability. And empirical means to do an experiment to observe things. So then we take sort of what we know about probability, but empirical is all based upon some kind of an observation, what has happened in the past. We use that a lot for sports. Statistics that they keep in sports, baseball or softball, they get you your batting average. How often when you get up to bat do you hit? And so that's an empirical probability. If it's you're a .348, that's a 34.8% hitter. That means you've got a 34.8% chance of getting a hit. It also means you have a fairly large chance of not getting a hit, right? Because that's how they rate them. So empirical probabilities we're going to see are things that have been observed. Theoretical are just based on sort of theory and may or may not be accurate. Okay. So then what we do is we've got to sort of mathematically get some kind of scale for probability, and it seems appropriate to use the 100% scale because something will either happen or it won't happen, right? So what's the chance of rain today? It either rains or it doesn't rain. Now it could rain heavily or rain, there's various things, but generally they're just, most probabilities it will happen or it won't happen. So if there's a 100% chance of something happening, then it will certainly happen. So if I walk outside and it's raining, I say, well, there's a 100% chance of rain today, right? And I'd be right, because it's raining. There's also, if you say there's a 0% chance, then that would indicate that it is impossible for that to happen. Now, because of all the mountains around us, we might say there's a 0% chance of rain, and it actually does rain because the weather changes. It just, based on the initial conditions, they thought it would be impossible to rain, but some stray wind blew some clouds over here, and we did get it. But typically, we would rate between 0 to 100, and then 50% is like equally likely to happen or not happen. Anything below 50% is less likely to happen than happen, and anything more than 50% is more likely than not. Okay, so it's kind of a sliding scale. And thinking of that, we had a unit on percentages. How do we calculate percentages? Do you remember that? So I try to get it here so it's all on the recording as well. Percentages. Oh shoot, this thing doesn't. Let's see if I've got my oops. Epic pen. I'll use this one. I don't like it as much, but it works. Where is it? Oh, here it is. Okay, so remember with percentages, we had percent over 100 equals is over of, or what I'm going to do is part over whole. So we can get a percentage by the part over the whole. The whole is, what are all the things that could happen, right? How many chances of something happening? how many chances of rain are there. The part would be the percentage of the days of probably rain, more likely to rain. So when we do this, we're going to see that calculating a probability comes right back to percentages. It's just counting how many total things there are. That goes in the denominator, that's our whole. And then how many things that we're looking to have happen there are. And it'll make more sense when we look at a specific example, such as, let's say we are going to roll a die. A die has 6 sides, numbers 1 through 6 on it, right? So to calculate a probability, oops, I can't write on the screen. So a probability calculation would look like, what's the probability, and a lot of times we go probability, of, say, getting a 3. We're going to roll a dice and get a 3. How many 3s are there on a, there's 1, out of how many different things that could happen? 6, there's 6 sides to a die. And so our probability is simply 1 out of 6. Okay, now you might say that's not a percentage, but it's not yet. If we take 1 divided by 6, and this one I've kind of I think I've got it right. I think we get 0.1666 repeating, so maybe 167. Plug it in the calculator and check it out. To turn this to a percentage, what do? We multiply by 100. So 16.67. So, and what you're seeing here is there's 3 different ways to write a probability. We could do it as a fraction, we could do it as a decimal, or we could write it as a percentage. 16.7%. Move the decimal over 2 places. So that's all there is mathematically, really, to calculating theoretical probabilities. It's count how many are there. There's 6 sides to a dice. Each side has 1 chance of happening. Again, assuming it's equally likely. Now, if the dice is not made correctly, it might not be that they're equally likely, right? Or if you put a little bit of extra weight on one side, like you want to go to the casino and try to game them, then it's not equally likely. So everything we talk about today, as far as theoretical probability, has the assumption that each thing happening is equally likely. And that's not always the case, right? Sometimes one thing's heavier than the other, or something might happen. But as far as the math, it's just, we're back to percentages. We just get a fraction of part over the whole. With probabilities, I say the good, and it's not always that it's good, but it's what we're counting, what we're looking for over the total. So you'll see me use this sort of thing. So it's, again, part over whole, good over total. So we're counting how many things could happen, and total, and then what are the things we're looking to have happen. Another thing you could do with the die is you could roll it and say, what's the chance of getting an even number, right? So we'll go probability of an even number. Well, how many even numbers are there on a die? 4-sided or 6-sided die?
Even? That would be just 3 then.
It's 2, 4, and 6, 3. So there's 3 of possibilities, 3 chances of getting an even number. What are the total? Again, the dice hasn't changed, it's still 6 faces. So probability of getting an even, we'd say, is 3/6, which is 1/2, which is 0.5, right? Which is 50%. So that's the 50-50 chance of getting even or odd. Okay, so that's probability. This is all theoretical probability, in fact. To do empirical probability, what we would do is we'd roll that die 100 or 1,000 times and see what actually happened. And then we would do the percentages based off of that. But theoretical, we just say, well, it looks like they're all equally likely. 1 out of 6, 3 out of 6. Okay, so far we good with the basic concept? Hopefully. We'll see. Oops. How do I? There we go. Oh, I got to clear my screen. That's why I don't like this one.
What
Yes.
would be the course we take after this class?
A math class?
Yeah.
You're done. This
Oh.
is the last math class you'll ever have to take, for your bachelor's at least. You may need to, depending upon your major, you may need to take a statistics class, and that's why we include kind of 2 units of statistics in here. The statistics we'll cover will be like the first 2 weeks of a statistics class if you need it. Okay, but the majors that are designed to have this as a course, this is the only math class you need to get the bachelor's degree in that field. Now, if you change your major or something, you might need more, but other than that, this course is designed to be the one, it's called the liberal arts type course. Most, sociology, a lot of majors anyway, this is all you need. But that you want to talk to your advisor about. So you don't need to take any more math classes unless you're in another major that this wasn't really the course you were supposed to take, because otherwise you should have taken college algebra, because then that leads you into the more technical fields. So it's kind of like if you're going into a technical field, they have algebra, pre-calc, and those kind of things. If you're going into a non-technical type field, this is the math class. And that's why it's really just a survey of math. We expose you to a lot of different things, and we go from there. Okay, so with theoretical probability, we do something called an experiment, and that the experiment is what I would say rolling the die 100 times. It doesn't really seem like a scientific experiment, but that's exactly what we're doing. Is we're just getting data, rolling the dice, seeing how many times we get a 1, how many times we get a 2, so and so. So we do experiments. That's how they developed the field of probability. Flip a coin. You flip a coin a couple thousand times and you see what happens. And then, this is some vocabulary. We have something called sample space, and the sample space is all the data we recorded. So we might roll the dice 1,000 times, and we will record how many times we got a 1, a 2, 3, 4, 5, 6. That's our sample space. Okay. The event is what we're looking for. Like on the question before, I said, what's the chance of getting a 3? That would be the event, rolling a 3. If we don't roll a 3, then the event didn't happen. If we roll a 3, the event happened. Or the event might be rolling an even number. And if we roll an even number, the event happened. If we don't roll an even number, the event didn't happen. So, and we use that from within the sample space. And then what we find is, kind of like I said, is we're thinking of probability as there's, whatever we're talking about, there's 100% chance of something happening. It either rains or it won't rain, but it's got to add up to 100%. It can't be more, it can't be less. Because if it's more, we haven't defined our sample space right. If it's less, we forgot to count something. Oh, we forgot about hail. That's not really rain. It's not raining. It's, so whatever we want to call as far as our weather shots, it has to include, it all has to add to 100%. So I just want to highlight, just from when we were doing earlier, I think it was chapter 4, exponentials, that 1 equals 100%, right? If you take 1 times 100, you get 100. So 1 or 100%. So if we deal with things as decimals, we'll use the number 1. If we use them as percentages, we'll use 100. I typically like to use percentages because it's easier for me to do the math than to work with 0.37. I'd rather work with 37% and work with 100. But both will work. Okay. So here it is. Just like I said, we're just counting. It's the number of things in our event divided by the total things that can happen. So I just shortened this to good over total, or I don't know, maybe good's not the right word, but what we're looking for over the total. Okay, we're just counting. That's, in fact, when I was studying to be an actuary, I was working on a master's degree in that, and decided I had a friend who was an actuary who was coming to be a teacher, and he says, you don't want to be he told me about what it was like. You sit down in this little office and you do math all day. I said, I don't want to do that. But I took the whole probability series, so probability was my major. And even at the graduate level, my professor would just say, probability is just counting. If you can count and make a fraction, you can do probability, even at the graduate level. So that's how we're going to calculate them. Again, we can write them as fractions. Again, probability of getting a 3 on a roll of dice was 1/6. We can write it as a decimal. 1 divided by 6 is 0.167, or actually 666 repeating. Or we can write it as a percentage. So these are all the probability of rolling a 3 where the event is a 3. So 3 different ways to write it. When you're going through the homework, sometimes they will want it one way or the other. Sometimes they want it as a fraction. Sometimes they want it as a percent or as a decimal. Again, my preference is percentages because it's just easier for me to work with personally. Fractions can be cumbersome. And when I use fractions, I actually I'll show you, I don't like to do reduced fractions, because if you don't reduce the fraction, you've got the actual of what's actually happening. Once you reduce that fraction, it kind of becomes more abstract. Okay. So, they are talking about rolling a 3. So we already, I was a little bit ahead, but I kind of go through. So probably rolling a 3 or an even number. I guess I've done this presentation too many times. We've already gone through those solutions. So, the sample space was, we could roll a 1, 2, 3, 4, or 5, or 6. That's all the options. You can't roll a 7. You can't roll a 0 unless you change your die, but, right? There's only one way to roll a 3, yeah. So the number of events of rolling a 3, there's only one of them, so that's 1. There's 6 possible outcomes, so the sample space has 6, so that's 1/6. So again, just getting more technical with the language, but it's just like what we thought. We just count the good over the total, or what we're looking for to happen over the total. Rolling it even, again, we talked about it's 2, 4, 6, so there's 3 options that could happen. Out of a total of 6, 3 out of 6. And again, I would actually like to leave it as 3, 6, because that physically tells us what's happening. There's 3 chances out of 6. If I take it down to 1/2, that's still the same probability, right? 50%. But now it's 1 out of 2. This could refer to flipping a coin as easily as getting an even number on the die. So my preference, again, it might not be the math system or math people, but I'd prefer to just leave it as 3, 6. Or use a percentage, 50%. Of course, you're welcome to do anything. So now the other thing we get into a lot with probability, again, rolling dice, flipping coins, and drawing cards out of a deck of cards. How many of you are familiar with what a deck of cards contains? Not everyone is. I grew up playing cards. Good. So a few of us. If you're not, deck of cards has numbers 2 through 10, and then they have a jack, queen, a king, and an ace. Sometimes the ace they count as a 1, but otherwise it's usually count. They call things face cards. That's anything with the jack, king, or queen, because they've got faces on them. And each of those, there's four sets of things. There are 2 that are black cards, clubs and spades, and 2 that are red colored suits, hearts and diamonds. Okay, so I think somewhere in here there's a little picture of what all 52 cards are, but that's kind of it. So to be able to count them, you have to know what's there. So the probability of being dealt a king. Well, how many kings are in a deck of cards? Well, since there's 4 suits, each suit has 1 king. There are 4 kings. Oops. Well, they did it for me, but let's back up. So we'll just think through it. There's 4 kings out of a total of 52 cards. So the probability is 4 out of 52. Again, that does reduce because 4 goes into 52. You could do it as 1/13, but I sort of prefer to leave it as 4 out of 52. Okay, so 4 out of 52, which also reduces down to 1/13. You could also plug that in your calculator and get the percentage. I don't remember what that one is. It's small. It's maybe like 2 or 3%. 1 divided by 13. Anyone got a calculator out? Let's go ahead and see what it is. What you get,
0.076.
0.076. So multiply it by 100, you'll see that's 7.6% chance. Okay, a little bit better than I thought. So the chance of getting one king, randomly drawing it out of a deck of cards, is about 7.6%. Okay, how about getting a heart? Well, that's the other thing, is that a heart is one of the suits. There are 13 cards in each of the suits. So 2 through 10, and those other ones we mentioned. So for getting a heart, we're going to get 13 out of 52, and 13 goes into 52 4 times, so that does reduce down to 1/4. Sometimes that's easy because I know 1/4 as a decimal is 0.25. So that means we have a 25% chance. And again, these are all correct ways of talking about the probability. Again, really just counting. So to be able to count something, you need to know what it is. And again, that's one of the things is culturally, there's some people, some cultures, cards are for gambling. That's not right. So you might not have not only never seen them, you might have had them outlawed. The other thing is there's also different types of cards. In this class, I had someone doing a project on card counting, and she did all this stuff, but the one thing she did is she was at her grandpa's house and she just grabbed his decks of cards, and he happened to have pinochle cards. Does anyone know what pinochle cards look like? They're not your standard deck. I think they're all face cards, or they don't have the number. They're different. And so they're great for playing blackjack because you almost always get either 20 or 21 with a pinochle deck. But I don't know, and I've never played pinochle, so I don't know how it works. But again, there's different things. Okay. So, and again, this one we can list as 1350 seconds, 1/4, 0.25, or 25%. The probability is just count how many of the things we want to have happen, count the total number, divide them, and we're done. Okay.
You go into 52?
Yeah, it's one of those that I would have never known it unless for cards, because I go, what, 13 can't go to 52? Oh yeah, I can, 4 times. Okay, and you think of it physically because there's 4 suits, and each suit has 13, and that's how they end up with the 52 cards. Okay. The same thing happens when so that was kind of theoretical probability. Okay, theoretical is that there's 52 cards and they're all equally likely to happen. But if like my house, we had 5 kids, and sometimes one of the kids would play with the cards and had a jelly sandwich, and then so you get cards that stick together. It's not as they're not as equally likely, right? Because so what you do is you do empirical probabilities, which is you actually count. So you would sit around all day and draw cards and see what the chances are. The thing is that the calculation's exactly the same thing, but instead of just counting what theoretically should happen, you're just counting how many things actually happened. Now, if you do it 100 times, what do you think is going to be more accurate? If you do it 100 times or if you do it 1,000 times? Let's make it a little easier. We're going to flip a coin. What's the probability of getting a heads? 50%, assuming you don't have a 2-headed coin, right? So yeah, so heads or tails, should be 50%. If you flip it 1 time, how many heads could you get? 1 or 0, right? Could happen or not happen. So then you would, if you do that calculation empirically, if you flip a head, you did it once out of 1 flip, that's 100%. If you got a 0, 0 out of one flip would be 0%. But if we did it 10 times, what do you think? What would we maybe get closer to? If you flip a coin 10 times, you might be getting closer to 50-50. You might get 6 heads and 4 tails, or you might get, so it could be different, but we would expect it probably. And that's the thing with probabilities, is that they come out over a large period of time. Now, have you ever flipped a coin and 3 times in a row you got all heads? Okay. Now, probability says that's not as likely, but it can happen. That's the thing with probabilities. You could flip a coin 10 times and 10 times in a row get heads. It's possible. It's not real likely, but it possibly could happen. So when we're doing an experiment, what the moral of the story is you have to do it a lot. 100 might not be enough, because you do it 100, I do 100. Our data might be very different. I might get a lot of heads and you get a lot of tails. Okay, but if we both did 1,000, we would probably be more likely to be close to it. And that's what we'll get into that more when we get to statistics. That's what statistics is about: collecting a lot of data, and then we can kind of get there. Okay, but all it is, it's really the same thing: good things over total things, except this time the good things are not by counting necessarily theoretically, but counting what actually happened. Okay, with this we could use it for basketball games. What percent free thrower are you? And we count how many times you shoot a free throw, how many times you make a free throw. Observe values, that's what it is. Baseball, football, whatever, all those statistics are empirical probabilities based on watching that particular player. How do they do in this season? Okay, and then they predict, well, if you do, you're a 95% free thrower, you're always going to get it. But what could happen? You could get injured, and that could change. Because again, probabilities are all based on what's been observed. They're based on the past. The past doesn't always mean that that's what's going to happen in the future. Okay, so we're going to do another type of empirical probability, and again, this gets us towards statistics. Is we collect a lot of data, and then we take that data, and there's going to be one question that we do in the quiz that's kind of similar to this. So we've got our data. What they did is how many men were sampled, how many females, and then they asked them whether they were married, never married, if they were divorced or widowed. And so we've got these values. If one person is randomly selected from this population, and so we've got a total of 242 people here, find the probability that the person is female. Well, female, it doesn't matter whether she's married, never married, divorced, widowed. What's important is that there was 124 females out of a total of 242 people. So again, if it's all being randomly chosen, probabilities would tell us that we'd have 124 chances out of 242 of randomly picking a female. Okay, so again, it's just observed values over total values. And again, probabilities to me make more sense because you get all these different fractions, right? Maybe that it certainly will reduce, but turning that to a decimal and then to a percentage, to me, makes a lot more sense. So 124 divided by 242, I come up with 0.512. So if we turn that to a percentage, that's going to be, move it over 2 places, multiplying by 100, that's a 51.2% chance. And that kind of feels about right. If it half men, half women, a few more women here than men, so that's our probability. And we are going to look next week, we're going to do a similar type table like this, but we'll do something called a conditional probability. So it gets a little bit more advanced. At this stage, we're just counting, we're observing, and we're getting a total. Questions? Doing okay? So what would be the probability of, I don't know what the next question is going to, what would be the probability of randomly choosing a divorced male? Male that is divorced.
Over everyone?
Yeah, if we're just going to randomly choose 10 out of 242. So probability 0.04. Okay, that was quick. Of a male that's divorced, I'll just do it that way. 10 out of 242, 0.04?
Yeah, it's like 0.0431.
0.0431, so about a 4.3% chance of that happening. Okay, so you can see we could ask any probability we wanted, and we'll do this with conditional probabilities next week as well, a little bit more advanced stuff. Okay, yeah. Okay, and they just, yeah. So they do all the work here. And remember, you have access to this PowerPoint, not a big deal. So that's it. Got one more thing to consider, I think, is expected value. I'm going to give a highlight, and then we're going in the quiz. Question 5 is an expected value question. Okay, so there's not a lot. This is what we use for in insurance, games of chance. The one thing we have about expected value is it's not really the value you expect to happen, and it only applies if you have a large number of chances. So some of the questions in the homework may say, you're playing a game, you buy 5 lottery tickets, what is your expected value? That's really not an appropriate question to ask. What's an appropriate question to ask is, out of the whole lottery, what's the expected revenue for the lottery company? Okay, so, but let me just kind of highlight what we do with expected value. So, first of all, it's like a situation. Let's take for insurance. So there is a, let's say, a 90% chance of a person driving and not having an accident. So we'll do that in A, no accident. There is a, and I'm just making all this up, so don't quote me on this. Let's say there's a 7% chance of a minor accident. We'll do an MA. And there is a 2% chance of a, what's a little bit bigger than minor, but not devastating. Well, we'll call it a bad accident. Okay, so minor accident, then this is a bad accident, and then there's what's left. Is that 100% yet?
No.
No, that's 99. There's still a 1% chance of it ruined my day. I had this happen, it's a total accident. The car has been totaled, completely destroyed. Unfortunately, I just got new tires on it, and they don't take that into account. When they pay you, when the insurance company says, oh, we don't care you got new tires, I just put $400 on my tires, they only gave me $2,400 for, you know, it's like I could have had bald tires, I would have got the same amount. But anyway, that's different. So there's these probabilities. So let's say no accident, what kind of damage would be done if there's no accident? Well, if there's no accident, there's no damage, right? So that would cost $0. What would a minor accident cost? So we'd say on average, a minor accident, how much do you think a minor accident might, like a fender bender, you got to get your fender straightened out or something?
Probably like, 200?
3,000, 2,000. Actually, you're probably right with these days because your cars are all plastic now. And
because you gotta pay for the, what's it called, the insurance?
well, the insurance, but this is how they do it. So we're just saying the claim. What would the claim be? Oh, you might have to pay deductible. Yeah, let's go with let's make it, yeah, probably even a minor accident could be in the thousands. Well, it's just easy calculation, make it 1,000. Bad accident is going to be, you know, fender bender, maybe some serious body work, maybe 5,000. Again, try not to be too bad. But if we total the car, depends on what you're driving, right? You just got a new Tesla, then maybe it's 100,000. Yeah, so let's just say it's maybe an average 30,000. So that's a big deal. So what the insurance company does is they want to get the expected value of what they might need to pay out. Okay, so what they're going to do is they're going to, and they could do this based upon how many policyholders they have, but what they would do is for expected value, you take the percentage. So for no accident, that's 0.9, and you multiply it by the value of that event. So 0.9 times 0. It's not going to cost the insurance company anything. Minor accident, and we'll pretend that these figures are what the insurance company has to pay out. There's going to be a 7% chance, so that's 0.07, that they're going to have to pay out $1,000. For a bad accident, which happens 2% of the time, that's 0.02, and that gets multiplied by the value of a bad accident, or the average value, right, 5,000. And then there's a 1% chance, which is 0.01 times 30,000. So if these were the figures, what the insurance company does is they do the calculation, right? 0.07, there's 3 zeros, 1, 2, 3, so this is going to be a $70 cost. 0.02 times 5,000, let's see, we move it this way, 50 times 2 is going to be $100. And then 0.01 times 30,000 moves the decimal place over 2, that's going to be $300. What this is doing, this expected value, is that for each policy, this is about how much they would expect that the cost would be. Because they're going to do maybe 100,000 people that they're going to insure, the per person cost, that's really what expected value is getting at, would be $470. So what does the insurance company need to do to make sure they can pay out these claims? They have to charge a premium, the policy, they have to charge people at least $470. This is the cost. But does that mean that they're going to charge $470? No. They want to make some money, so they're going to add their profit to it. They've got overhead, so these are just payouts, right? That's what they use expected value for. This is what, if they get all this data collected, if this is accurate data, this is what they would expect to pay out for each policyholder. Again, some policyholders they're paying 0. Some they're paying 30,000. But the expected value says the probability, that brings in the probability of things happening. Okay, so this is going to be the base premium. And that's what actuarials do. They sit and they calculate these things. They actually go out and they have to collect the data because it's only as good as the data you have. Then they also say, okay, how much does it cost to run our company? We've got overhead, so maybe they add 100 for that. We're going to pay insurance agents to sell this, and they're going to want a commission. We got to add to that. And then on top of that, the company wants to make a profit. So that's why you don't pay $470 for your insurance for the year, right? You're $1,200, $1,800. And again, I just made up these figures, so I don't know how accurate. There's probably less than, hopefully there's less than 1% that is having a total accident. It's probably a much lower amount. But that's the process of calculating expected value. And we'll do another one. It works with lotteries because you can win certain different prizes, and what's the probability or percent of winning each one. You take the percent times the value of the prize, and you add all those together. That will give the expected value for like a casino. Casinos do this. They let some people win, because if nobody wins, who's going to come back, right? You see someone win 150, maybe it could be me next time, right? That's why people go do it. So they have to let some people win, and they want to make sure you don't lose too much, but they like when you lose, but they don't want you to lose too much, because if you lose too much, all your money's gone and you're not coming back, right? So anyway, That's probabilities, and I think that's the last slide. So let's clear this off. It's time for working through. Let's see. We'll end the slideshow. We'll go back and we'll do the quiz. Actually, let's keep going here. Mini lesson. Again, the mini lessons are there if you want to work through them. They've got videos and stuff. The homework we'll come back to. Again, get that to 70% and you're good. The quizzes, this 5 questions. So let's go ahead and work through these. And remember to get 2. So on this one, let's see, let's make it a little bit bigger. How would we do this? We've got a spinner, and we're going to pretend that there's a spinner here, that if we spin it around randomly, what would be the probability that it lands on a number greater than 3? What's that? 9/12. So there's 9 numbers that are bigger than 3, and there's 12 total numbers. Does that make sense? Does that seem reasonable? And what concept are we using to be able to do this?
When could you explain it again?
Sure.
I got 9/12.
Okay. So we've got 12 slots. 1, 2, 3. So it's like a clock. So that's where the 12 comes from. And then we're going to have a number greater than 3, not equal to 3, greater. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. And so again, it's all just counting and doing, so it's 9/12. And they want it, but then they're going to want it as a reduced fraction, which I don't like, but because I like 9/12, it's very clear. 9/12
right?
would be 3 goes into 9. Well, so 9. Let's do this. 9/12. 3 can go into 9, and 3 can go into 12. 3 goes into 9 3 times. 3 goes into 12 4 times. 3/4. 3/4. So that's the answer they're going to check, or they're going to want in here. Which was also 0.75 if you do that, which is 75%. But the fact that all of these little slices are equal in size. If one was bigger than the other, then they would not be equally likely, right? So this is, all the sizes are pretty much equal. We'll check our answer.
Yeah, what time is the club again?
What's that?
I'm a bit ahead. You go.
Yeah, it worked. And again, you might have a different question. They probably have the spinner, but they might ask a different question here. But again, it's counting. How many slices would fit that divided by the total number of 12? Okay, so we'll go to number 2. And this one's talking about a deck of cards, well-shuffled standard deck of 52 cards. Determine the probability that the card you select is an 8. Okay, so how many 8s are there in a deck of cards? 4 of them, right? A club, a spade, a heart, a diamond. So there's sometimes when we use the number, so the 8 is the type of card, but there are 4 of them. How many cards total? 52. How many cards are in a 52 deck card? There's 52. And so it's 4 out of 52. Write your answer as a reduced fraction. And remember, 4 does go into 52 13 times. And you'll kind of get used to that, hopefully, as you go through.
Actually, which one was the club again? Was that the king?
Well, the club is a suit. So there's a club, a spade, heart, and a diamond. So those are the suits. So each card, like an 8, will have 4 different suits.
Okay. And the club was that the clover? The one that looks like a clover?
Right, yes. Okay, so as a reduced fraction, we want to put in 1/13. Then they're going to ask us to do it as a decimal, round it to the nearest thousandth. Thousandths is a third place, right? So 0. What's 1 divided by 13? Anyone?
0.0769.
Whoa. I got 0.58, but that's because my calculator didn't get cleared out. 1 divided by 13. Yeah, 0.0769. Now we're the tenths. Now remember with a little bit bigger. With where when we're counting places, it's tenths, hundredths, thousandths, so it's 3 places out. So it's 0.769. The 6 gets rounded up to 7. So they're going to want it rounded to 3 decimal places. Okay. Write your answer as a percent, round it to the nearest tenth. Well, that's why they want you to round it to the thousandth place. You can always go from a decimal to a percent simply by moving the decimal to the right 2 places.
Damn, still got it wrong.
So that's going to be 7.7. Okay. And again, your numbers may be different. They might have asked for something different. If they asked for a club specifically, there's 13 clubs out of, so I think that's how this problem is. Yeah. This one, we'll check the answer, and we're okay. Questions? Okay. So that's question 2. Go to question 3. So now the other thing we do with probability a lot is colored balls in a bag, and we pull them out and randomly. So for this particular jar, we've got 9 red, 5 white, 8 yellow. So how many total do we have? 9 plus 5 plus 8. It's 17, 22. Get that right? So find the probability of the given event. Write your answers as reduced fractions or whole numbers if, So what's the probability a red ball is drawn? Well, there's 9 red balls out of 22. That's a number that does not reduce, so that's good. The ball drawn is not red. It's not red. So this is kind of going to give us a new idea. We'll also do this more formally next time. Well, there's 5 white balls and 8 yellow balls. 5 plus 8 is 13 out of 22. Notice if you take the probability of not drawing a red and add it with the probability of drawing a red, what do you get? 22 out of 22. So that's kind of this. We'll talk about this property more, but the probability of something not happening is basically take 100% minus the probability of it happening. 40% chance of rain means there's a 60% of no rain. That's what it's supposed to mean. Okay. And then what would be the probability that a green ball is drawn? There's 0 green balls, so that kind of throws you what? Out of 22, so 0. So the way we can fill these in, this has to be a fraction. That's why they say as a whole number, right? This is 13 out of 22. And again, you may have a different listing of numbers here, but it's just, you have to add them together to get the total, and then it's the how many in the event over the total sample space. Okay, It's the third question. We've got 2 more left, and the last one will be okay. So this one I think is like the one we did with the randomly choosing a female out of a group. So we have males and females. Looks like they got grades of A, B, and C, so those are listed out of a total of 60 students. So then we're going to choose one student, chosen from random, determine the following probabilities. Write your answers as reduced fractions. So again, what's the probability of drawing a male out of this group? Do that. There's a total of 32 males out of 60. Again, we want to reduce that so we can see they're both even. 8/15. 4 can go into both. Yeah, you maybe see that. If you didn't see that, what I always do is I start with 2. I can see 2 will go into both of these. So I divide the top and bottom by 2. 32 divided by 2 is going to be 16. 60 divided by 2 is going to be 30. Oops, I can do it again. And so if you saw it was by 4, you'd get your answer quicker. 2 can go into both of these. 2 goes into 16 8 times. 2 goes into 30 15 times. And now those can't reduce. So there's also calculators that will reduce fractions for you. There's apps probably that will do it as well. But I think if you don't put it in reduce, it will not count it. So what's the probability that the student was female? Well, there's 28 females. Out of 60. And yes, 4 goes into 28 as well. So 4 goes into 28 7 times. 4 goes into 60 15 times. And you might be able to see that 7 plus 8 is 15. So we're counting them as either male or female. Okay. Student was male and got an A. So again, as we go through and counting, we're just going to, for that one, was male and got an A. So there's 20 out of the total of 60. And again, that will reduce down to 20 goes into 60, so that's, yes.
So when we're doing those ones, we do it with a total or not? Because like what I did is I looked at because it's asking about A. I did the 28 instead, so I wouldn't do that. That's the total I got, A.
We're going to do that next week.
Okay.
That's a conditional. That would be that they got an A and were a male. So that's a conditional. This one is just saying they're randomly chosen. What's the probability of getting someone who's a male and who also got an A? So it's not a conditional. What you're doing is, next week's stuff is conditional, assuming they got the A, so it would be out of 28. So you've got half of the next lesson already learned. Okay, so, but yeah, these are all going to be out of 60 because it's just a random choice. Student was female and got a B, so was female and got a B. There's 15 females who got a B. Again, out of the total 60, because this is not a conditional. So 15 out of 60. 15 does go into 60, so that's 1. How many times it goes? 4 times. 1/4. And that the student got a C. Well, it doesn't say male or female, so we take the total of students. There's 14 students who got a C, so that's 14 out of 60. And again, you can reduce this. 2 goes into both of them, so that becomes 2 goes into 14 7 times, 2 goes into 60, so that would be 7/30. Okay? Questions on that one? Okay. Okay. Now the last one will be the hardest one, but maybe not that hard. But it's the, and I actually won't even put all these in because those are good. Let's go to the last question is, This is our expected value question, okay? And they're doing a raffle. And we'll see how this one works. So the PTO, I guess Parent Teacher Organization, is selling raffle tickets to raise money for a classroom surprise. The raffle ticket costs $5. There is one winning ticket out of 190 tickets that were sold. The winner gets a prize of $84. And so now we're going to answer these questions. What is the expected value to you of one raffle ticket? And again, this is not, we'll do the calculation, but again, it's not an appropriate use of the thing of expected value. Okay, so what's the probability that you've got a winning ticket? How many winning tickets are there? How many total tickets are there? 190. So the probability of getting a winning ticket is 1 out of 190. Okay. What's the value of having that winning ticket? How much? Close. But to get that $84, your net value is $79. You're going to win $79, right? Because 84, you had to pay $5 to get into the game. So 79 is actually the amount that you'll win. Okay, so that's what we'll use here. So that's the winning. What we have to add here, those you might not get the winning ticket. How many chances are there of your ticket not being a winning ticket? 189. So if there's one winning ticket, there's 189 losing tickets out of 190. Notice that's a very high probability of not winning. And what's your value of not winning?
Wait,
-5.
where
You
did
will lose
get
5.
189 from?
Because there's a total of 90 tickets, 190 tickets. One of them is a winning ticket,
Oh, so that's just when they. Okay,
so 189 are going to be losing tickets.
So if you're adding, what was it? So we're adding the cost to enter the raffle. Then on top of that, we're adding the what's the likely chance of losing, and we're adding it all together.
Yes. And so we calculate these probabilities. We take 1 over 190 times 79, and you'll see the thing is with these, sometimes these numbers become really small. 1 divided by 190 is like 0.0052, and then we multiply that times 79. So this number here is 0.415. I'm going to round it to 4 decimal places, 58. This number is your chances of losing. So 189 divided by 190 is like 99%. You multiply that by 5. So that's negative. This ends up being negative 4.97. I guess since it's money, we just really need to go out maybe 2 decimal places. So you take that 0.4158, and you come up with that your expected value is to lose $4.56, right? To the nearest cent, $4.56. Now, any questions on that calculation? Probability of winning times the value of the win to you.
Oh, are you just rounding to the hundredths place?
Yeah, just to the hundredths place because the nearest cent.
Okay.
Yeah.
Yeah, that makes sense.
Okay. And you're either going to win or you're going to lose. Yes, sir.
So how did you even get either of those numbers to subtract?
this decimal here.
Yeah, how do you get that?
So I took 1 divided by 190
Yeah,
and then multiplied by 79.
okay, and then how'd you get the 4.1?
I took 189 divided by 190 and times it by -5. Okay. But what you're going to see is that this also will help us. So if we were to purchase 6 tickets, now what's our probability? Or what's our expected value? Well, this is the expected value for each ticket. That each ticket we buy, we're going to lose. You can just multiply. So this one's easier. It's just take,
You just multiplied the rounded version, right?
yeah, take 6 times -4.56. Now, again, in reality, you will either win or you will lose. If you lose $5, right? If you win, you get a net of $79. So one of those two things will happen for you. But this is kind of expected value. If you play it a lot of times, that's what expected value is about. So if you bought 6, again, you would either lose 6 times, or you might lose 5 times and win on the 6th time. But this is just like if you did this a lot of times and you averaged it out. That's what an expected value is. So we're going to take that, let's see, 4.56 times 6, I get 27.36. And again, it's still negative, right? It's still a loss. So most of these games of chance, on average, everyone has to lose. So that, because where does this lost money go? It goes to the organization who sold the tickets, and that's how they raise their money. And again, you say, okay, I donated $5. Maybe I'll win something back. And let's just make sure we get that's all right. What is expected value to the PTO of one raffle ticket? Now for them, oops, I forgot my negative up here. The thing is, the calculation's the same for them, except that when people lose, that's a positive for them. When the person wins, that's a negative for them. So it just changes the sign. So we actually don't have to calculate this. We just take the value of the first person and make it positive. So each ticket, they're expected to win $4.56. Okay, so see how that is? They're just on the other side of the table. They're collecting the money. If you're buying the ticket, you're paying the money. So that's kind of the nice thing about expected value, is it, if you do it from the other perspective, you just change the sign. And so if the PTO sells all 190 raffle tickets, how much would they expect to win, or have for classroom supplies? We do the same thing with the 6 raffle tickets. We just take their value of what they would win per ticket, and we would multiply it by all the tickets, 190. And again, at this point, you could also say, well, this 4.56 times 190. So they can expect, I get $866.40. And we'll just do a check to make sure. And again, that's positive for them. That's how much they would. So if they sell all 190 tickets, they'll have one payout, and the rest will be the $5 that they collect. Let's just check, because there might be a rounding error. Oh, good. We didn't even get a rounding error. We got them all correct. Okay. So in your homework, there might only be 1 or 2 expected value. You could probably get 70% without doing the expected value. However, it's also understanding expected value is kind of good, because it allows you, if you're going to try to do a fundraiser like this, you know what you need to charge. And you kind of, like, I've got a nonprofit. We had a dinner once. we didn't charge any tickets to come in because we figured people would donate more that way. But there were some people who donated and some people didn't donate. They just got a free meal out of it. We ended up at the end breaking even because someone wrote us a check for $1,000, but we had 30 people and not enough people contributed. So we broke even on that one. So I look back on this, I would say, yeah, we should have at least charged a $10 or a $5. But you live and you learn. So this just shows you some of the mathematics behind it. If you're going to do a prize, you've got to do these calculations so you have enough money to pay the prize and that you can actually win something, raise the money. And then that that, hey, if we sell 190 raffle tickets, we're going to make 860. If we had a budget that we need to waste 2,000, we've got to do this differently. We got to maybe charge more money or get more people or something. So that's what the math helps you to do. So expected value is kind of a nice thing. Again, you'll be able to survive without it, but I wanted to put it in there. And again, probabilities are really just how many things could happen out of the total number of things. And we just deal with fractions, percentages. And this one's pretty straightforward. And next week won't be much different. I mean, we're building with that same thing, but we bring in the conditional probability. What if we know this happens? There's a couple other things that we'll bring in, like two events happening in a row. What's that probability? So we'll get some more calculations, but they're going to be based on what we do today. All right. So we check the answer. We try to go to question number 6, and we can't because there's only 5 questions. So we are done. And again, you're welcome to start working on the homework if you want. You're welcome to take off and take a break, get some lunch, and or whatever you do. But get the homework done hopefully by next week. Thursday we have our lab day, so that's also a good day. If you're having any questions, come in. We can work together on things, either past or present stuff.